Yes. All right, we have a Hazel double header. So I am Cyrus. I am a postdoc at the University of Chicago for about a week and a half, and then I'll be moving to Michigan as faculty. David will be my student there, so I'm very excited about that. What David's been telling you about is these text-like user interfaces, right? And I think these are often great. I spend a lot of my time looking at a screen like this. I'm sure probably almost all of you do as well. And, you know, David's been telling you about other text-like user interfaces that we're trying to make as great or greater. But I bolded often there because there are times when it's not great, even with all the fancy stuff that David showed you. For example, say you're trying to insert a color. And this would be useful if you're doing live programming and you want to see the color of something, that background color of something, right? Well, you could certainly type out the color that you intend, right? And you'd be entering the number literals corresponding to the RGB and A values of that color. But this is about as good as a text editor can do, right? And this isn't great. Who can tell me what color this is? Yeah. Good. For my talk. To get to the point of this talk, what if we could fill these holes? Here the hole is kind of invisible, but pretend there's a hole there, right? What if we could fill those holes not by entering the text directly, but by manipulating an appropriate GUI, in this case, a color selector, like you might be familiar with from Photoshop or any other graphical tool. But if you could do that without actually fundamentally leaving the programming world like you'd have to if you used Photoshop. So that's the idea here. And so we actually, way back, my first project as a grad student at CMU was really actually looked at this problem. We have a paper about that at ICSI 2012. And there we implemented a tool that kind of allows this. We implemented it as an extension to Eclipse for Java, sorry. But anyway, the point is made regardless of what the tool and language is. What this tool allows you to do, this tool is called Graphite. It allows you to associate with types, in this case Java classes, these things called palettes. And when you pull up code completion in a situation where the expected type is color, in this case, in other words, when there's a hole in the internal representation that Eclipse uses for programs, then it shows you this option to pull up this interactive palette, and if you select that option by pressing enter, it brings up the associated GUI. It might look something like this. I think I just copied this out of Photoshop or something like that. And then you can interact with this thing using your keyboard and your mouse and by dragging along the color wheel, exploring. So that's what that color was, sort of royal blue or something. And then when you press enter, you're back in code world. You're not stuck forever in GUI world. So the purpose of the GUI, unlike most GUIs in the world, is not to have an effect. It's to generate code, in particular generate an expression corresponding to that color. Now, colors aren't the only example. They're just a good one. So another example that we explored in that paper is this regex helper palette. And so when you're trying to insert a regex, often that'll be something quite complicated. It's hard to reason mentally about, so it helps to get some documentation and actually interactively test that regex against some examples, sort of lay out what you want the regex to match, in this case these temperatures, and shouldn't match times and these things. And so you can do the same thing. You can associate with this regex pattern type this palette, interact with it, and when it's done, it generates the correct code for you. And in the case of this regex API in Java, the correct code is actually kind of subtle. You have to use this compile static method, and you have to double escape backslashes, and it does all that for you. So we actually did a little pilot study, which I won't talk about, which showed that there's some real benefits to this. Speaking of which, so the design methodology that we used here, consistent with it being an ICSI paper, was we did a lot of empirical work. So we actually started with a large online developer survey. We ended up with about 450 participants. And we gave them these mock-ups, like what I just showed you, and asked them for both quantitative Likert scale style feedback and qualitative feedback. And then we just solicited other use cases other than the ones I just showed you from these users based on their own experiences. We coded all that up. I'll show you the results in a moment. And then we implemented it. So we did all this mock-up stuff before we implemented it. Then we implemented it based on the sort of design considerations that that survey revealed. And then we did a really small pilot study with actual human subjects using that regex palette, n equals 7, but we sort of validated that this was useful. I just want to give I'll direct you to that paper for all of the details of all this stuff. I just want to give you a couple of highlights from this survey, which I think is a really nice method to get empirical data out of online population. So we showed them these mock-ups like I just showed you, and then we asked them to consider situations where you need to instantiate the corresponding class. What portion of the time do you think you would use this feature? And it turns out people were pretty excited, especially about the regex one. 36% of people said nearly every time, and then most of the time came in second. And the other examples that we gave, there's a SQL one I didn't show you, but the color example. People said some of the time, or most of the time, rarely. Very few people said never. And actually this was, we got from the qualitative feedback here, the color example was a little weird for people because they're accustomed to putting colors in style sheets, and a lot of their feedback was, I would never write a color literal in a program, and that's just because style sheets are not properly typed in Java world. So, and then, there was other stuff in that paper you can look at. We also solicited a bunch of use cases. We had 450 participants. We got a lot of use cases. We were actually able to categorize them into different categories. Here's just a smattering of examples that we got from that survey. There's lots of other ones. Music was another one that came up. And so this necessitated, we can't anticipate all possible use cases, so this necessitated a extension mechanism. So the way you actually associate these palettes with classes in Java was this annotation, and the palettes were just implemented as little web widgets. Anyway, so the details are all in there, but so to summarize, what that prior study did was it established the usefulness of this technique. It established that there's a wide variety of use cases, and it developed a little extensibility mechanism. Now, 7 years later, we're thinking about this again as we're designing another programming environment, and there's a few things that were limitations in that prior work that we want to address. So these limitations, there's no persistence, there's no compositionality, and there's no liveness, are things that when we implement a similar mechanism in Hazel, which we're calling Livelits for reasons I'll describe in a moment, we really want to check off all of these boxes. The first two, we're just going to defer to the existing studies that I just talked about, right? They're as relevant to the mechanism that I'm going to describe. Our extensibility mechanism is different, but achieves extensibility. And then I want to talk about these last three things. So let's start with persistence. So I showed you this example just a moment ago. What happens when you're done interacting with this user interface is you press enter and there's this code there, and then that user interface is gone forever. And so that's a problem if you want to edit that regex, add new test cases that you want to look at, and so on. And so in that prior paper, we had this really ad hoc method where you could select the code that was inserted, and then the regex palette would be responsible for parsing it and reinstating itself. And so every palette had to have its own ad hoc Java parser in it, which is terrible. So, but that's the best we could do in this environment. In Hazel, when we're going to do something similar, what's going to be different here is that these palettes, which are now called livelits, are actually part of the syntax tree. They're not sitting on top of the user interface and then generating normal code. They're actually a part of the syntax tree the same way the let bindings and function definitions and so on are. And so this color palette here, it is generating an actual color value, the RGBA value underneath, but it's doing that while maintaining the fact that that color value came from this user interface in the AST. So when you save this, when you load it again, that user interface state will still be there. So it's not ephemeral, it's persistent. And the way we achieve this is by, Well, so what's not happening is we're not saving the actual state of the user interface. The way livelits are implemented are using this model view update, kind of a variation of the model view update model that you might be familiar with from Elm and other functional languages. So a livelit consists of a type. That's the type of expression that it's generating. And then it has a type for models. This is the internal model of the UI. A type for actions that the UI can generate. An initial model, an update function that like responds to actions to generate new models. A view function that generates the actual the view that's shown in the GUI. And then what's different, what's unique about livelits is there's also this expand function, which takes the model and generates the underlying expression that livelit application will behave as. So livelits are displayed according to the view, they behave according to the expansion, and they're stored only according to the model. So the view is not stored because it can be recomputed as needed from the model, and the expansion is not even stored because it can be recomputed from the model, although you might want to store it just as an optimization. All you're storing is the sort of abstract model. So because there's this expansion function that's generating code, livelits are really a fancy macro system. I actually explored a similar idea in my thesis work, which was published at ICFP last year, which was basically a very similar idea, except the UIs were strictly textual. There was no GUIs in live programming and so on, but you can go check out this paper for a very similar system in terms of there being an expand function that's responsible for handling this GUI, which happens to be just the textual GUI for interacting with HTML. What's different here is that it's graphical, and there's a couple of other things that are different that I'll talk about now. So the second problem that I mentioned previously is that there's no real compositionality with the palettes mechanism that I showed you previously. So what you can do in that mechanism is define a palette for example, a table of grades. But that table can only itself contain other closed expressions. So numbers and string literals are fine, but if you tried to, for example, create a more Excel-style user interface where there's a formula box and you wanted to type 91 times curve, where curve is a variable in scope here, you wouldn't be able to do that with any help, at least from the programming environment, because it's not compositional. It's just as soon as you're in the GUI, you're in the GUI, and you can't go from code to GUI back to code. Like this box containing 91 times curve is not an expression box, it's just a text box in that prior system. In Hazel, that's not true. So it's compositional in the sense that you can splice expressions into GUIs. So you start at the top level with an expression, then you have a GUI, and in that GUI there can be more expressions. And because, like I mentioned before, livelits are themselves expressions, they're persisted, you can even do interesting things like put a livelit inside another livelit. So if you want to explore you don't have the final grade yet, but you want to explore what would happen in the rest of the code that I'm not showing here, you can put a little final slider there. And that final slider is generated by applying another livelit, this $slider one, which is a parameterized one that takes the min and max. The way the layout works, or will work, this is obviously a mock-up, is that the name of the livelit is always shown in sort of the expression position, and then the GUI for the livelit has to go somewhere, and there's different options for where it can go. So normally it'll go in a separate box below the line in which it appears, but a livelit's going to override that, and in this case it'll show the actual GUI in the cell and the formula, the expression up top, like that. Not super important, just wanted to point out what was happening there. Okay, so this is compositionality. This is you start with expressions, you have GUIs, the GUIs can have expressions in them, those expressions can have more GUIs in them, and it's turtles all the way down. And then there's one more component if you really want to have this sort of Excel-style livelit. In Excel, you have a formula box, but then the actual box that the formula corresponds to contains the value of that formula. And to be able to compute the fact that 91 times curve might be 95, you need to be able to evaluate that formula during editing. And evaluation interlaced with editing is live programming. So we need to be able to support that. We can't just have strictly sort of static user interfaces that you have to finish the whole program and run, and then you get an output. You want to be able to run as you go. And as David described at the beginning of his talk, we've been working on that problem. We had a paper at Popple this January on that problem. And I will just refer you to that for how we solve this. But basically, the idea is you can run these programs, even though there's a hole, for example, here. Still, there's no hole here. There's no number here. There's just a hole in the final position. You can run these programs. This will work even if this whole expression here is underneath a binder. If it's inside another function that's been called multiple times, there will actually be multiple closures that you can toggle between. And all that work was described in our prior work, so I will, for the sake of time, refer you to that. But the point is, live programming integrates very deeply with these livelits. That's why we're calling them livelits. So livelit stands for live literals. They're literals in the same sense that like a list literal is something that is an alternative user interface for list expressions that appears directly in your program. These are live literals in the sense that one, you like interact with them in a live way, but in a more technical sense because they support this kind of live programming. So there's here's another example which I think I have time for. It's another example involving grading because you're thinking a lot about the first class I'm going to teach in a week. Say you've finished computing some weighted averages, not shown, and then you want to select grade cutoffs. So here, you might want to do that on a number line by dragging around these little toggles. But you want to actually see the grades. You want to see the value of weighted averages, not just the fact that there exists some value weighted averages that will appear when you run the program. And so this allows this palette, this livelit, to plot these orange dots, this liveness feature. Okay, to summarize again, we developed this work in 2012 that really kind of got at the heart of this idea, and now we're refining it to support these additional things that I think will really allow us to do some, come up with some more cool examples. And this is work in progress. This is just kind of a progress report. We're working on all this, so in true Hazel fashion, we're working out the theory of this whole mechanism in Agda right now. We're working on the implementation. We sort of had one that's been kind of broken for a while, so I'm not brave enough to do a live demo today. I mentioned briefly about these layout variations that we're thinking of. We want to do a lot more case studies. And then I have these out there ideas about how to turn this mechanism into a full-on authoring environment that's rooted in programming. Like, what if everything in the document was an expression, and just some of those expressions were graphically represented using livelits, instead of there being kind of a dichotomy between the things in the document, like images that are just their own ad hoc thing, and programs. So ask me more about that. If you see me, I'll be here all week. Thanks. You can go to hazel.org for more on the whole Hazel project, and I will leave this example up because it really points to a lot of the different things I talked about while I take questions. get up to that livelit is basically the result of evaluation